Okay, so we're talking about the mechanics of solid materials. So what we did last time was we started with the spatial local form of linear momentum balance, and provided that's satisfied, we derived an expression called the principle of Dilember, or in the case of quasi-statics, principle of virtual work, that is essentially equivalent statement, but not as a differential equation, but sort of an integral statement. Okay, so it's not the integral spatial form of linear momentum. It's something else, but of course they imply each other. Now, then within the principle of Dilember, there appears an arbitrary vector W. If we choose that vector to be the velocity field, then we found out a special equality, which says that the amount of power you put into your deformable body, and that power is from the external forces like traction or the body force, goes into rate of change of the kinetic energy, and also part of it goes into the work per unit time that is required to actually deform this body. Okay? So you can imagine that if you have a rigid body, this term eventually, of course, should drop out. But in general, we do have a deformable body, and this term will survive. So this expression, which is a specific case of principle of Dilember, by the way, is called the mechanical energy balance. Now, within the mechanical energy balance, there appears the internal power, and we express that in a number of different ways. In particular, we had what we call the stress power. So the stress power integrated delivers you P internal, and stress power is, for instance, S dot E dot or P dot F dot, or there are all other forms, but the nice thing about these expressions is that you see a measure of stress and measure of deformation, and the rate of that deformation appears as the conjugate variable with respect to the stress. Okay, so that's the nice thing about these two particular expressions. And finally, based on that expression, we argued the following. We said, okay, we can take a closed path, or we can take a arbitrary path in the strained space, and we try to monitor the amount of work that is done over that path, which may or may not be closed. But eventually, we argued that what we should have is that, well, first, I'm talking about an elastic material. Elastic material is one that depends only on the present value, right, of the strain and not on its history. That's the general case, as we argued before. So that is the definition of an elastic material, but that is not sufficient actually for the stress power to eventually, let's say, integrate to zero over a closed path, or for it to be path independent in general. The stress actually has to come from a potential, and that potential is the strain energy function. Okay. So that was a major conclusion that we reached. And afterwards, we argued, well, okay, so in general, the strain energy function is always there, but the material I have, irrespective of the particular form of W, so it can be isotropic or anisotropic. And if it's isotropic, there will be eventually there can be multiple functionally significantly different looking forms, and we'll see examples to some of those. But in general, it can be isotropic or anisotropic. But in the case it's isotropic, which essentially means that the orientation of the eigenvectors of E doesn't really play a role, what we discussed was that W needs to be a function of the three eigenvalues, and I indicated that with a hat, actually. The three eigenvalues of the Lagrangian strain tensor, or for that matter, the right Cauchy-Green deformation tensor C. They're really equivalent statements, from which you can derive, really, using that expression, the form of S. And the form of S is the following, where alphas are actually scalar functions of the tensorial variable E and of its eigenvalues eventually. So this is an expression where first we see kinematic nonlinearity because I am choosing a particular measure of stress. I am choosing a particular measure of strain. It's not any particular choice, any random choice. It's this one. It's the Lagrangian one. Plus, there is the material nonlinearity, which means that this is not linear in the components of V. In fact, even if you had this much, it's already nonlinear because what goes into alpha 0 is in general a highly nonlinear function of the components of E. Okay? So that's where we pretty much left. Now, but that is the general form, and the particular form that pertains to a given material depends on the form of W that we choose. And that's what we would like to discuss today. Okay? So what are some examples to the strain energy function at finite deformations? And to make the point, and namely the main point here is that in the kinematically and materially nonlinear regime, there isn't a single functional form for the strain energy function. That's the point that I will make. To make that point, first I'll start with the small deformation setting where there is functionally a single form, okay, for an isotropic elastic material. And then we will appreciate how hyperelasticity, right? Hyperelasticity differs from linear elasticity. So let's give some examples to isotropic strain energy functions. So, as I said, I'll begin with case 0. This is not large deformation. It's going to be linear elasticity. And it is very instructive because it turns out this is the starting point, actually, even for writing down nonlinear elasticity relations, hyperelasticity relations. So in the linear case, everything is neat, sigma equals C epsilon, right? And for the case of isotropy, I can write kappa trace epsilon identity plus 2 mu epsilon deviatoric, as we've discussed earlier. Okay, where K is the bulk modulus and mu is the shear modulus. So now what we would like to discuss is, or we would like to express the material behavior, model it in terms of, from now on, the strain energy function. Because we have to have a strain energy function, and the reason is that, right, the stress has to be derived from it. Otherwise, if I write directly S as a function of V, it might be that there is no potential that delivers it, and then if I do a closed cycle, the network may not vanish. Okay? So it's important that we express first the strain energy and then derive the stress from that. So what is the strain energy in the linear elasticity regime? There has to be still one, because the only thing that distinguishes this regime from the case of hyperelasticity is the specific assumption of small deformations. Okay? So this should be, in fact, a limiting case of an expression that takes into account large deformations. Then if I invoke the small deformation assumption, I should fall back onto that case. And since the large deformation case requires that there be a strain energy function, there should also be a strain energy function in that case. In fact, that's exactly the case, and I'll discuss that also in the next item. So what is the energy in the small deformation regime? This, of course, you will remember as well from undergraduate mechanics. So you do a test, you measure stress, force versus deformation, okay? Let's say displacement, and you monitor the network done for that elastic deformation. That will be the area under the cycle, so that will be 1/2 PU. And now if you're interested in the amount of energy stored per unit volume, then you can divide that by area and that by the referential length, and that will be your strain, that will be your stress. So it will be 1/2 sigma epsilon So work per unit volume will be 1/2 sigma epsilon. And that's exactly what the strain energy function also gives us. Okay? Okay? So if we go back to this board over here, right? S dot E dot, for instance, right? In the purely elastic case, would be del W over del E dot, okay? And in the purely elastic case, that is equal to W dot. And P internal is an integral of that, okay? And that's the net power, or without the rate integrated over time, that would be the net energy. So that's W integrated over the referential volume. So W is energy stored per unit volume, okay? And that's exactly in the small deformation regime, 1/2 sigma epsilon. So, but because we are in the small deformation regime, let's indicate or distinguish that with a different symbol, not a W, but something like a omega, if you like. And that's now equal to 1/2 sigma epsilon. And in a three-dimensional setting, we have to work with the tensor stress and strain, but the expression is going to be similar to the 1D case. Okay? So 1/2 sigma dot epsilon. Then you can go ahead and substitute this expression over here, and you'll find that right, that's the strain energy function. And let's call that the infinitesimal strain energy function. Okay. This is the functional form of the strain energy in the small deformation setting. There is no other form for every material that behaves elastically in the small deformation regime. This is the form of the strain energy function, okay, or the strain energy stored per unit volume. Now, what is it that distinguishes one material from another? Well, two things. One, the form of C. Is it isotropic, anisotropic, and what type of anisotropy you have? And even if you have the same type of anisotropy, what are the values of the constants? So the expression for C is what distinguishes one material from another. Okay? So that's what you need to determine for a given material. But once you determine that, the function is quadratic in epsilon, and C goes in there as your constant tensor. There is no other expression. Okay, let's keep that in mind. Well, we may want to simplify this expression a little bit. This is true isotropic or anisotropic. But in the case of isotropy, I have a special expression for the stress. Let's plug that in. So I have 1/2 stress dotted with strain. So kappa trace epsilon identity dotted with strain plus 2 mu 1/2. The 2's cancel. 2 epsilon deviatoric dotted with epsilon. Okay. Now, identity dot epsilon, that is trace epsilon, so you'll have trace epsilon squared. And now what you have here is, well, you can write epsilon in terms of its spherical and deviatoric part. The spherical part dotted with a deviatoric one will be null, because the spherical part contains an identity. Identity times the deviatoric will extract the trace of this part, which is by definition 0. Okay? So this is equivalent to epsilon deviatoric dot epsilon deviatoric. Okay? You can fill in the blanks yourself. So therefore, what we have is a neat expression for the infinitesimal strain energy function for the case of isotropy. Okay? Now, as I said, so the infinitesimal case should be the special. We should capture this as a special case of a more general, completely nonlinear framework, nonlinear formulation, kinematically and materially. But we don't know what that formulation is yet, right? We know this one because this is so neat. There is a unique expression, unique functional form. In the case of isotropy as well, a unique functional form. And there are only two constants. And the only thing that distinguishes two materials from one another are the values of these constants, okay? This form does not change from one isotropic elastic material to another one in the small deformation setting. So that's what's so nice about this, okay? Now, however, since this has to be the special case of a more general nonlinear setting, this, in fact, now we're going to interpret these terms and this expression. This expression is going to, in fact, form the basis of formulating the nonlinear expressions. We don't know what they are yet, right? All we know is that this should be a specific case of that general nonlinear formulation, and we need to yet develop it, right? Now, to make that development, it's very useful to interpret these individual terms because they've been instrumental in formulating the nonlinear forms for the strain energy function. So let's think about what these individual terms are. Remember, kappa is something that relates volume change to pressure, and this has to do with pure shear. So in fact, if you look at the individual terms as well, this is something that has to do with volume change, trace epsilon, as we've discussed before. It's change of volume per unit volume. So therefore, right, this thing is something that has to do with volume change, and indeed it's called the volumetric part of the infinitesimal strain energy function. Okay. Remember also that the determinant of the deformation gradient tensor J in the kinematically small deformation regime, it's equal to 1 plus trace epsilon. So trace epsilon is what governs the volume change. And pure shear does not induce a volume change. So you can have pure shear that does not influence this term at all. Okay? So this is entirely independent from shear in some sense. Whereas this term, the shear modulus appears there, should somehow have to do with pure shear. And there are multiple ways of arguing that, non-rigorously, but nevertheless to argue that. So one is if you take actually a simple shear, let's say all the components are 0 except the 1,2 component, that's you just take something and shear it, okay? That would be simple shear, and the diagonal components are 0, the trace is 0. In that case, trace epsilon, there is no such contribution. If you look at the stress, all the contribution will come from 2 mu epsilon deviatoric. So that's a simple shear situation where epsilon deviatoric is non-zero, but trace epsilon is. Now, so therefore, one eventually argues that epsilon deviatoric is what governs shear. And indeed, it is so. You might remember from your undergraduate mechanics, so now this is beyond the content or our goal within this topic, but epsilon deviatoric is indeed what governs shear, because you might remember from undergraduate mechanics, when you try to formulate criteria for deformation or failure, within the context of plasticity, let's say. So you have an elastic deformation, and then at some point, there is the onset of plasticity. And you covered this in the topic of failure criteria. So you want to remain in the elastic region, and let's say plasticity is for you, say, failure. And you had a criteria called the von Mises criteria. Now, when you formulated that criteria, it was in terms of the components of the stresses, etc. But if you go ahead and carry out that expression or evaluate that expression by replacing the components of the stress in terms of the components of the strain and these elastic moduli, what you will see is that epsilon deviatoric precisely appears in that expression. So epsilon deviatoric is what governs the onset of plasticity. And you know that theoretically, plasticity should not be due to pure pressure. The material cannot deform plastically because it requires shear stresses to move dislocations. So epsilon deviatoric is, again, something that you interpret as what governs shear deformations. So to make the long story short, this is what you can very neatly interpret as the deviatoric part or the shear part. And hence, if you look at the expression for the strain energy function for infinitesimal elasticity for isotropy, you see a neat decoupling from volumetric and shear effects. Okay? Pure shear is represented by that. Pure pressure, let's say, or volume change is represented by that, and they act independently, right? So somehow there is no contribution from volume change to that expression, and there is no contribution from shear to that expression. Okay? So we call that volumetric deviatoric decoupling. That, however, is a very, very special, actually, situation. It is rigorous for the case of linear elasticity, but it turns out in the case of hyperelasticity, general nonlinear elastic deformation, that is not a necessity. Now, although it's not a necessity, people have been inspired from this decoupling, and when they first developed expressions for the strain energy function for hyperelasticity, they also proposed a similar decoupling, okay? And you're going to see that explicitly in the upcoming examples. Okay. Now, all right, let's move on now to hyperelasticity. What we would like to do is propose expressions for the strain energy function for a material that deforms elastically, but a lot. And the first proposal is actually something quite simple. And it's directly inspired by what we have in linear elasticity. Well, the idea is, well, in the linear elastic regime, I have the measure of stress, measure of strain, and they're related to each other through some fourth order tensor. Well, in this case, I'm looking for S, just like sigma, it's symmetric, and I have E, just like epsilon, it's symmetric. Well, in the linear case, they're related to each other by a fourth order tensor. In this case, let me also relate them to each other through a fourth order tensor. The question is, what is that fourth order tensor? I can here write anything, but then I have to remember that if the deformations are small, the expression should necessarily fall back to what I have there, because the small deformation formulation characterizes precisely the material behavior when epsilon and hence S is small, right? So whatever goes in there should consistently represent the limit as E goes to epsilon and S goes to sigma. And hence I don't have any choice here, okay? The simplest thing, if I want to put here a constant tensor, in fact, the only thing I can put is actually the stiffness tensor. Okay? Again, the requirement is I want to put something constant. Okay? And as E goes to epsilon and S goes to sigma, I want to necessarily recover the linear elasticity relation. That is a requirement. That is a consistency requirement. We're not going to dwell on it too much, but I'm mentioning it once. And I'm going to give you other examples to that consistency requirement. Okay. Consistency in the sense that the formulation should capture the linear elastic expression. Okay. Okay, so I'm not going to discuss in depth, but perhaps you are already convinced that it better be so. So now, that's nice. Well, there are two things that are nice about it. Well, first of all, I don't need to do some additional experiments for the large deformation regime to find what C is, because I already know it from the linear elastic setting. Two, yes, I am specifically interested in isotropy, but this expression would, of course, hold also for anisotropy. Okay? So, and formulating stress-strain relations or hyperelasticity strain energy functions, in the case of anisotropy, it's not trivial at all. So that's one really nice thing about that expression. It makes that quite straightforward. But Now, if I am interested in linear, in isotropy, well, again, this expression necessarily has to recover what I have in the linear elasticity setting, and therefore, I should have exactly the same equality, right? So kappa trace, not epsilon, but E, and 2 mu deviatory part of E, okay? So then we can proceed by the calculation of the strain energy function, following similar steps similar to what we have done for the linear elasticity case. I can plug in the expression for the stress into the expression for energy per unit volume, okay? And then you can go ahead and plug in the particular expression for S. This is always true, whether or not it's isotropic. But now if I use the isotropy expression, then you recover again a generalization of the expression for linear elasticity. Okay, so the question is, how is this different from linear elasticity formulation? Let me actually clarify that in a second. Okay, I'm going to discuss it a bit further, and if you're not convinced, please ask that again. Okay? Now, we do have to notice that this is a very, very specific case. It is a proposal, okay? And as I said, there is actually, as we will see shortly, there isn't a single functional form for the strain energy function, even in the case of isotropy. So you're going to see many different forms with arbitrary numbers of constants. Linear elasticity, only 2 constants in the case of isotropy. In the case of hyperelasticity, even if it's isotropy, you can have an arbitrary number of constants, an arbitrary number of different functional forms. That's the difficulty with the case of nonlinearity. Okay, but we can easily see that this necessarily is not general, because in the case of isotropy, this is the expression for the stress. And the stress, as I told you, it's not necessarily linear in the Lagrangian strain. In fact, from the outset, there's a quadratic term. Okay, you see only linear terms, right? So that is indeed very specific. Okay. So we are in the kinematically nonlinear regime, which is expressed through the use of the large suitable measure of strain, not epsilon but Lagrangian strain, and a specific choice of the stress. But material nonlinearity, the general possibility for material nonlinearity, is not reflected. You, in fact, omit it and you propose a linear expression. But we have to remember that that linear expression is in terms of S versus E. If you look at the relation between, let's say, the Cauchy stress and E, or for that matter, the Cauchy stress and, let's say, the Eulerian strain, Almanzi strain tensor, they will not be linear. Because to calculate the Cauchy stress from S, I multiply with F transpose, divide by J, etc., which introduces orders, orders that are higher in E than the linear. Okay, so the relation stress versus strain depends, the linearity depends on the particular choices I make. For these choices, it appears to be linear. Okay? But kinematically, we are always in the nonlinear regime. Now, why is it important that I am choosing, or how is this different, or how is this advantageous compared to the formulation in the linear setting? So in other words, why can I not, let me put the question in the reverse manner, why can I not use the linear elasticity expression when the deformations are large? And that's something actually I have talked about before. Okay? So to make the point, let me tell you when this one is suitable. This one is suitable, this expression for stress versus strain, which is a very, very specific case, is suitable when the deformations are, or the strain, let me say, is small. Okay? the strain is small, and when I mean strain, I really perhaps want to refer to the stretch, okay? So you have a material that cannot stretch a lot, okay? If the strain is small, well, perhaps it would be suitable to replace E with epsilon, and if strain is small, stress is going to be small, so all measures of stress are perhaps small, so then I can put here sigma, and that makes sense because I end up with sigma equals C epsilon, which is precisely the linear elasticity regime, okay? However, what if the stretches are small, but the rotations are large? In that case, when the rotation is large, despite the fact that I have small stretches, the measure of strain in the kinematically infinitesimal regime, in other words, epsilon, will not be small. And that's what we discussed earlier. When deformations are large, epsilon will be large. And in fact, even for a pure large rotation, epsilon will be non-zero. And then your expression for linear elasticity will predict a stress, which is absolutely not true, okay? So that's where the advantage of this one comes in, because E filters out rotations. It does not take them into account. It only retains what has to do with the stretch, okay? And therefore, will again give you a correct measure of stress, even if the rotations are large, okay? So large rotations, but small stretches. And good example, a very good example actually to that is the paper that I have in my hand, okay? So I can pull on this paper, right? Have a look for a second. Right? I can pull on this and we don't see any visible deformation. There will be a stress, there is a certain strain, but they are small and hence sigma equals C epsilon holds. Perhaps it's anisotropic, right? But now, as I pull, if I also bend it, and if I try to use sigma equals C epsilon, because epsilon is going to be significantly large due to the rotation, okay, of the material line elements or material surfaces within on this paper, the stresses will be nonsense if I use sigma equals C epsilon. Whereas, if I use this expression, it will be predicted correctly because rotation will be appropriately filtered out of this deformation, and S will predict whatever has to do with only the stretch part, okay? And the stretches are small, and hence S will be predicted according to this relation, which is like the infinitesimal one, except that rotations are taken care of properly. So good examples are fabric, okay? Like your shirt, if it's not super elastic, this one is not, right? It cannot stretch too much. Paper, thin sheets in general, or perhaps ropes. Of course, again, it depends on what it's made of, but if it's not very soft, then it can deform a lot, right? You can make it rotate a lot, but you cannot stretch it a lot. So that's a very, very suitable expression to use in that case, okay? And in terms of the strain energy function, that's what you're dealing with. All right. Now, okay, so finally, one more remark. What if the deformations are indeed large, okay? So if this doesn't hold. If this holds, this is a beautiful expression that one can safely make use of. It will be actually predictive capability-wise, it will also be quite accurate, okay? But if the deformation is large, then probably the stress-strain relation is not going to be linear. In general, it's not. That's what we see theoretically, and this is linear, so its predictive capability will be limited for a material like rubber or tissue, biological soft tissue, etc. And in that case, it's not something you can make use of. If you try to make use of, it doesn't even make so much sense, because in that case, trace epsilon will be very, very large because epsilon is large. It doesn't even represent volume. So the interpretation of this as a pure volumetric part, it's meaningless because at large deformation, volume change is not through trace of the Lagrangian strain, but through the determinant of the deformation gradient, J. Okay? And this one is not something that only has to do with shear, which means that if you take something and deform it a lot arbitrarily, the shear, the volume change part that has to do with J will actually appear partially in here, and the shear part will perhaps make a contribution to that term. So the equality functionally is meaningful, or let me say it's apparent, the relation to the infinitesimal case, but the interpretation becomes meaningless when the deformations are large, all right? So therefore, this at large deformations obviously has several, let me say, limitations. So then the obvious question is, what's the next step in the levels of complexity towards a more general formulation of hyperelasticity? Something that can fit eventually experimental data better, right? And with respect to that, we should realize that, again, with respect to experimental data, the data is stress versus strain. In the linear elasticity regime, you see a line, and there is only one way to deal with a line, and that's through the slope, okay? And that's the stiffness tensor. But in the nonlinear regime, you take one isotropic material, it might look like this, you do a test, you take another one, it might behave like that, you take yet another one, it might behave like this, etc. So in other words, the expression for the line, because it's highly nonlinear, can have arbitrarily complex, let me say, it's the way it looks can be arbitrarily complex. Okay. Now, so suppose you write different functions for S versus E. Okay. Obviously, none of these are as such, because this predicts a linear relation between S and E. It's a line. So none of these are such. So suppose you propose functional forms that look like this, like that, or like that. Which one is better? Well, the question is answered through experimentation. What you are actually on the background interested in is an experimental result. You take a material, piece of rubber, you pull on it, okay, and you collect data. That's your data. So the line that now you should pick is one that fits that data, right? So what distinguishes the quality of this green line from this blue line, apart from the qualitative differences, is the fact that one fits your material data well and the other one is not. So you would go ahead and pick the green one. So that makes the difference between two different functional forms. So in order to make sure that you can fit, of course, the data well, you better also have sufficient number of constants in your formulation. Because if you have only two constants, you don't have much degree of freedom. The more constants you have, the better you can fit complex data, right? So eventually, when we make this transition, we want to make two things. One, I want to avoid a linear relation between S and E. Okay? That's the first step, and that's the first step we will take. The second step, as soon as I accomplish that goal, I want to put in more than two constants, because the more constants I have, the better I can fit experimental data. Okay? So let's proceed along those lines. And the first model we're going to pick is one that still retains two parameters, but it now incorporates a highly nonlinear relation between stress and deformation in terms of S and E. I have only two parameters, so those two parameters are actually immediately enforced by the consistency condition that I mentioned before to be the linear elastic parameters kappa and mu, right? Because when J becomes small, it goes towards 1 plus trace epsilon, and this term will have to do with epsilon itself, or epsilon deviatoric dot to do with itself, actually. So eventually, when you enforce deformation to be small, this thing will collapse precisely to the infinitesimal strain energy function. Hence, these constants have to be kappa and mu, right? So I have only two constants, but now you see that j appears in there. It appears in a logarithm, powers of j, etc. Okay? Now, it turns out you still make the interpretation that this is a pure volumetric contribution and this is a pure deviatoric contribution. And that interpretation comes in two different ways. One way will eventually appear when I eventually derive the Cauchy stress in terms of the left Cauchy-Green deformation tensor. Okay? But before we get there, which will require first deriving the second Piola-Kirchhoff stress tensor from this strain energy function, we can see that J is what governs volume change at large deformation. So it appears in here. Now, it also appears in here, but what you can notice is I have a tensor here, trace of a tensor that looks like j to the power 2 over 3 c, and c is f transpose f. If you calculate the determinant of that, it's equal to 1, okay? Which you can show on your own. So volume change, which is characterized by j at large deformations, it's filtered out of this expression in some sense. And hence, this filters out volume change as pure deviatoric. This one incorporates only volume change, right? So again, right? So we are doing something very similar conceptually to the infinitesimal strain, infinitesimal deformation setting, but the measures of deformation I'm using are different. So let's derive the stress, which is del W over del E. And it's going to be composed of two parts. Derivative of the volumetric part, and then the derivative of the deviatoric part. And we can call this number 1. And let's call that one number 2. And work on the terms individually. So first, term number 1, I'll do that in detail. And the second one will follow from this one. So I'm trying to take the derivative of the volumetric contribution to the strain energy function with respect to Lagrangian strain. The Lagrangian strain is 1/2 C minus identity. So what I can do is I can actually take a derivative with respect to C, but because there is a factor of 1/2, it appears in there. I throw it up here as a factor of 2. Okay. So that's what I now have to calculate, this term. And that's convenient because the expression is in terms of C and not E. All right, so the volumetric part, we have 1/2 K ln J squared. So we're going to have 1/2 cancel with that 2. We're going to have a K. We're going to have a ln J. And then ln J squared, the squared will come over here, and del ln J over del C. Okay. That's the derivative of the volumetric part that I've written. Okay, so if we continue further, we have K ln J. Derivative of ln J with respect to J first, that would be 1 over J, and then derivative of J with respect to C. Okay. Now, this is the term that I have to deal with. Now, if I was trying to take the derivative of this tensor, the determinant of the tensor with respect to itself, then I know what the result is, but J is not the determinant of C, but rather it's the square root of the determinant of C, because this is F transpose F. Okay? So let's just quickly, therefore, take care of that. The third invariant of C, square root with respect to C. So that's 1/2 square root of determinant of C, determinant of C with respect to itself, okay? And from an earlier homework, you will remember that this is determinant of C C inverse. Okay. We also used that expression last time, okay? Or a similar expression. All right. Now, moreover, determinant of C is J squared, right? And therefore, here I have J, okay? So if you cancel everything out, so let's write it here. It's equal to 1/2 J C inverse. That's del J over del C. And I plug that in here. The 1/2s cancel. So we obtain K ln J C inverse. Okay. Then we proceed with the second term. And this one proceeds along similar lines. I'm almost going to give you a full, actually, derivation here. But we've already obtained one critical result here. We're going to make use of that. So del W over del deviatoric, again, is going to be twice the deviatoric part derivative with respect to C. Okay? And now you can go ahead and take the derivative of that expression. So you have mu, let me just write down the result for you, minus 2 over 3. So I'm dealing with the first term, j to the power minus 5 over 3, del j over del c, and then there's trace c. And then we deal with the trace c term. So we have j to the power minus 2 over 3, and then del trace c over del c. Now, del j over del c is something we've already calculated. Del trace c over c is identity, okay? So you can rearrange this, simplify it slightly, and you will find that it's equal to 1 over 3 trace C, C inverse, plus identity. Okay. And we're done. All right. Now let's put them together. So S is equal to the sum of the contributions from the volumetric and the deviatoric parts. The volumetric contribution is K ln J C inverse. And after switching the order of, in the second term, we have identity minus 1 over 3 trace C, C inverse. Okay. So that's the expression for stress. And now you see that there is absolutely not any sort of linearity between S and E, or for that matter, between S and C. This is a highly nonlinear relationship. Okay. All right. Now, but S, remember now, is not a physical stress. It's just some mathematical construct that we're using, and it's very nice because we now know, by now, that when we take the derivative of the Lagrangian strain with respect, strain energy function with respect to Lagrangian strain, S is what we recover. So mathematically, it's very, very useful, and modeling-wise, it's very useful, but the physical stress is the Cauchy stress tensor. All right? So we are interested in that. Okay? Now, that's what we're going to calculate. Let's first notice the following. C, remember, is F transpose S, F. And FF transpose is B. Okay? And we remember that one of them is expressed as U squared, whereas B is expressed as V squared. Right? These are the symmetric positive definite tensors that appear in the polar decomposition of F. Right? And they share the same eigenvalues. And hence, C and B share the same eigenvalues. And therefore, their traces, which is the sum of the eigenvalues, have to be the same. So trace of C is the same as trace of B. Okay? Okay, so since once we've observed that, now let's proceed. T is 1 over J, F, S, F transpose. And I'll just multiply that expression through these additional terms. So we have K, ln J over J, F C inverse F transpose. All right? And again, mu J over J, so that would be J to the power minus 5 over 3, F transpose. So FF transpose goes in there. Minus 1 over 3, trace of B, F, C inverse F transpose. You dropped your lens. How did you manage it? Okay, so now FC inverse F transpose is equal to identity, right? Because F transpose F inverse, that would be F inverse F minus transpose. F transpose, they cancel those terms. That's an identity. This one is an identity, all right? And this one here, it's B, all right? So we have K, kappa, ln J over J. That's a factor, multiplying identity, plus mu J to the power minus 5 over 3. And this is B minus 1 over 3, trace B identity. This is precisely the spherical part of the tensor B. B minus the spherical part is the deviatory part. And that's equal to T, right? So now you look at the expression for T, and you see two parts. One part is traceless because of that. The other part is spherical, okay? So this is the deviatory part of T. And this is the spherical part of T, okay, as a whole. And now we know when we talk about the stress, the spherical part is the thing that has to do with, let's say, hydrostatic setting with pressure. This one has to do with shear. And hence, we again have an interpretation where, based on the strain energy that we've proposed, and there we already interpreted the two contributions to be volumetric and deviatoric or shear-related contributions. Those eventually lead to a decomposition of the stress into a pure volumetric and a pure deviatoric or shear part. Okay. 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 So that is a nice also result. So we're looking at a hierarchy of models. Small deformation, linear elasticity, let's think only isotropy. Neat form, 2 constants. What's the restriction? Deformation has to be small. Then I ask myself, well, I want to deal with somehow large deformations, but large in the sense that rotations are large, stretches are still small. Can I still have a rigorous expression? Kirchhoff-Semmenon, okay? But now that's just a functional expression. Okay, it works in this case, but what if the deformations are really large? Then I better have a nonlinear relation between S and E. I go to the next step, the neo-hook material. But what's the restriction with that? Okay, it's nice, nonlinear, but I have only 2 constants. I cannot fit my material data with 2 constants. So now what I need is a model that has the whole nonlinearity plus an arbitrary number of constants. So that takes us to the last level. Now, this is not the end of the story. This modeling of elasticity at large deformations is a challenging issue that, from different perspectives, is still actually going on today. So people are dealing with this challenge. Okay, but let me give you one final example within the hierarchy of examples that I've expressed. One final example that has been quite successful. And it's called the Ogden model. Again, it's based on the idea volumetric plus deviatoric. Okay? It doesn't have to be necessarily so, right? It doesn't have to be necessarily so, but that's a typical assumption, right? Now, it's a typical assumption, again, to highlight for 2 reasons. One, that is the decoupling in the case of linear elasticity. But there's actually another reason, and the other reason is the following. So first of all, the volumetric part will be some function of J because that's the measure of volume change at large deformations. In the Ogden model, you can choose it to be the one from neo-hook, okay? The one that has to do with the logarithm of J. You can choose the same one. Or if you want, you can choose another one, K over 4. J squared over 2 ln J minus 1, for instance. That's another one. And there are still other ones that are used to express the volumetric contribution. But almost always in the volumetric contribution, within such a decoupling idea, there's always only a single constant. That's the bulk modulus. Okay? And the reason why people don't dwell so much on the volumetric part, but rather concentrate on the deviatoric part, actually has a physical interpretation. And the physical interpretation is that typically materials that can go large elastic deformations are actually incompressible, which means that their volume cannot change. Again, an excellent example is rubber. So in the linear elasticity regime, it's characterized by the Poisson ratio, which is very, very close to 0.5. Okay? Doesn't change its volume. So which means that K will blow up towards infinity. So in that case, for this thing to remain finite, J has to be very, very close to 1. Okay? So in that case, the contribution from the volumetric part will actually be negligible compared to this part. The contribution from this term to the stress will, of course, be significant. K will be large. It will multiply some terms. They will be small. Large times small will be finite. But remember, in the strain energy, the measure of deformation goes in terms of higher orders. So that term will actually vanish. It will go to 0. And that's rightly so because the material cannot change its volume, and hence you're not storing any energy due to volume change. And therefore, this part is sort of only conceptual. And it has numerical purposes as well. You need to have something there. Sometimes in a numerical setting, the particular choice you make might even influence the robustness of your algorithm, etc. But the physics is really in the deviatoric part, because if the material cannot change its volume, how is it going to change its shape? Through shear. And that's how it's going to store energy. And the shear part is reflected in here. So you have to model this part very carefully. This is how you fit experimental data. And that's why here also there's only one constant, but here now there will appear, right? That was our goal, many, many different constants, right? And the particular choice of the Ogden material. And one says Ogden material. There is no Ogden material. I should say Ogden material model, right? The material model for the deviatoric part in this case is as such. So let me first write it. So P, there's a sum over M contributions. There are constants mu P and alpha P. And there appear eigenvalues, capital lambda 1, 2, 3. I'll tell you what it is. Raised to exponents alpha P. And these exponents are the same exponents. So each one has the same exponent. And the lambdas are the principal stretches. So this is the deviatory contribution. It should be insensitive to volume change. If there is pure volume change, this thing should not contribute to energy change. Or if there is no shear, let me say, this thing should not have any, well, I repeat, if there is no shear, this thing should not have any contribution. So we should extract the we should express the stretches with respect to a tensor that does not have any determinant, or determinant of 1, let me say. And this is that tensor, j to the power minus 1 over 3f. So determinant of this is equal to 1. Okay. So if I could have pure volume change and no shear, W deviatoric is 0. Right? So that's why you extract these lambdas, plug them in there, and now I have two m variables, m of these, mu p, and m of these, alpha p, okay, 1 through m. If the deformations become small, this contribution should collapse to mu epsilon deviatoric dotted with itself. It has to. That is a consistency condition, okay? Because it should capture the linear elasticity setting as a particular case when deformations are small. That forces a restriction on the values you can choose for these constants, okay? And that restriction is so if you know the linear elastic material behavior, you know what mu is, so you actually have 2m minus 1 independent constants here. All right. Now, from this now, you have to, of course, in practice, calculate what the stress is. That is somewhat lengthy, and we do not have time for it, so we're not going to do it. But let's quickly interpret what this means conceptually. What it means is, suppose I had only a single expression here, not a sum, but let's say m equals 1, right? In that case, mu and alpha, okay? And mu times alpha has to be equal to 2 mu, and therefore I again have only one variable, okay? Mu and kappa that characterizes the material behavior. So it is nonlinear, but still it has only two constants. So then it would be as though I have a representation for the referential configuration, right? Because from this, I'm writing referential because from this I derive the second Piola-Kirchhoff stress tensor which lives sort of on the reference configuration. So I have only one constant, right? M is equal to 1. So using that, I derive the stress, okay? But if I do that, I cannot really have I will get a stress that doesn't fit my material data well. So I add another, let me say, branch. I look for m equals 2. When I say m equals 2, now I have 4 parameters, mu1, alpha1, mu2, alpha2, subject to that restriction. So overall 3. So it's as though I have another referential configuration representation. And here I have another contribution to the stress. And then if I have m branches, really here I have m representations of the referential configuration. And together they represent my actual referential configuration from which I consider or derive the overall stress. So I have the overall behavior, which are contributions from individual representations, if you like, of the reference configuration, and together they sum up to deliver me what the final stress is. This is, of course, just a schematic way to describe how this function works. In principle, you are interested only in the stress result. For that matter, or for that purpose, this is just a function. You take its derivative, proceed with the stress calculation. Okay? But I think that's one interpretation that is sometimes useful to develop theories that are, let me say, more complex. Right. All right, so if not, so where are we so far? We're in the special topics section, and we're seeing how continuum mechanics plays a role in expressing ideas from quite different fields in mechanical engineering in a concise manner. It helps us, let me say, see the big picture, let me say, clearly, I think. It does away with some of the mass, but of course there are always some remaining complexities, and some of those complexities we are dealing with in these special topics. So we started with rigid bodies, large rotations, no stretches. Then we looked at linear elasticity, small deformations, small rotations. And here now we're looking at large deformations, stretches and rotation-wise, right? And now we are therefore in a most general setting. We are expressing the material is deformable, and hence stress is directly related to deformation. And we have models for the relation between stress and strain where there appear some constants. And these constants come from experiments. I find them so that the relation between stress and strain fits the data points well. Okay? And that is a phenomenological approach. I am at the engineering macroscopic level, and I propose a model. This model has a rigorous theoretical basis, but at some point I have to propose something for this thing in a quiet, let me say, experience-based manner, so that I know, based on my experience, this form is able to fit the experimental data quite well. Does it always fit it perfectly? No, right? But it's a very, very good model. But in general, you might ask yourself, even in the case of linear elasticity, well, there are these constants, and these constants I have to do experiments for. Is it possible to determine them without experiments by abandoning this phenomenological level and falling back sort of to a lower, an alternative level, where I deal with the complexity that lies underneath this macroscopic level, the structure of the material at the microscopic level, let's say its atomic structure, and predict these constants, okay? And next time, we're going to see how continuum mechanics plays a role in predicting the constants that you see in these experiments. But as I said, we're going to fall back to a different phenomenological level, because there we're going to make use of things like atomic or molecular potentials, which one has to do separate experiments for. But at least now we're at a different level, and I can use something that has been devised in a relatively general setting to predict something else in a completely different setting, at a macroscopic setting. So it is, in some sense, therefore, called a non-phenomenological, or let me say, non-experience-based approach, right? And I think that's quite nice, and we're going to see how, again, the tools that we've developed so far will help us at least express the main ideas in this goal, okay? So that's the topic for next time, and I'll see you then.